Welcome to The Explainer. Today, we're going to pull back the curtain on the internet. We're talking about the hidden rulebook, the set of instructions that literally makes our entire digital world work.
It feels like magic, doesn't it? But it's not. So let's start right there with that one single click and follow the insane journey it takes, racing across a global network of billions, and I mean billions of devices.
All right, so to really get how brilliant a solution is, you first have to wrap your head around the problem. I mean, think about it. How do you possibly bring any kind of order to this digital chaos of computers, phones, servers, all growing every single second? Just try to picture this. You're trying to send a letter, but there's no postal service. No addresses, no zip codes, zero rules. That's pretty much the chaos we were dealing with. So the big question was, how do you make sure your message doesn't just disappear into thin air?
Well, the answer is actually this really elegant, universally accepted set of rules called the TCP/IP model. This is it. This is the official rulebook. It's the postal service that literally the entire internet agrees to use. Okay, so let's break this down. This model, it's basically a 4-layer stack, and this stack is the secret sauce. Each layer has one very specific job, and when they all work together, they take that digital chaos and turn it into the reliable internet we use every day. So right at the top, you've got the application layer. This is the part you actually interact with. When you're typing in a web address or sending an email, this layer is getting your data ready. It's like writing the actual words in a letter before you stick it in an envelope. Okay, one layer down, you've got the transport layer. Think of this as the super organized postal clerk. This layer looks at your data and decides how it's going to be sent. Is this super important, needs a signature kind of mail, or is it more of a just drop it in the mailbox and cross your fingers situation? Then we get to the internet layer, and this one is, well, it's absolutely essential. This is where your data actually gets its address. It gets chopped up into these little things called packets, and each one gets an IP address stamped on it. It's literally the to and from on the envelope. Without this step, your data would be completely lost. And last but not least, the network access layer. This is the physical part. The delivery truck, the mail plane, the whole shebang. This layer takes those digital packets and turns them into actual physical signals. Electricity for cables, light for fiber optics, radio waves for your Wi-Fi, and physically sends them out into the world. All right, so now that we have the layers, let's zoom in a bit. How does this whole digital postal service actually manage to get the job done so fast and so accurately? Let's look at the mechanics. Okay, remember that postal clerk, the transport layer? Well, it has two main ways to send things, TCP and UDP. TCP, that's your certified mail. It's all about reliability. It sets up a connection, checks that every single piece arrives, and makes sure they're in the right order. You absolutely need this for stuff like loading a website, right? You can't have missing pieces. Then there's UDP. Think of UDP as a postcard. It's way faster because it just fires off the data and doesn't wait for confirmation. This is perfect for, say, online gaming or a video call, where a tiny momentary glitch is way better than a long lag. So, with billions and billions of devices out there, finding just one would be like finding a needle in a global haystack. That's where subnetting comes in. It's basically the internet's zip code system. It groups all those addresses into smaller, local neighborhoods, or subnetworks. That way, a router doesn't have to know every single address on the planet, it just needs to know which neighborhood to send the packet to. It makes things way, way more efficient. Now, most of what you do online, it's what we call unicast. It's super simple, one-to-one. Your computer talks directly to one server. That's it, like sending a private email just to one person. But what if you need to talk to everyone nearby? That's a broadcast. It's like making a public announcement over a loudspeaker in an office. One message goes out, and every single device on that local network hears it. And then you've got multicast, which is this really clever middle ground. It's not one-to-one, and it's not one-to-all. It's one-to-many. A single message goes out, but only to a specific group of devices that have said, hey, I'm interested. Think of a live video stream. It only goes to the people who are actually subscribed and watching. So this system, it's amazing, right? But it had a huge problem, a massive flaw baked in from the very beginning that honestly, nobody really saw coming. And it all had to do with the addresses themselves. Here's the deal. The original system, IPv4, had a limit of about 4.3 billion unique addresses. Now, back in the 80s, that sounded like an infinite number. Who could possibly need more than 4 billion? Well, we did. It's just not enough for today's world.
Yeah, we came up with some clever tricks, but honestly, those are just temporary fixes. The bottom line is, we've basically run out of addresses. So this crisis, this running out of room problem, it meant we needed a brand new system. And that led to the creation of its successor, Internet Protocol version 6. You've probably heard of it as IPv6. And let me be clear, IPv6 is not just a little update. It is a monumental leap. First, the address shortage. Solved. It gives us 340 undezillion addresses. That is a number so big, it's hard to even describe. It means every grain of sand on every beach on Earth could have trillions of IP addresses, and we still wouldn't run out. But it's more than that. It's also designed to be more efficient, and maybe most importantly, it has much better security built in right from the start. And when you put them side by side, you really see what a huge deal this is. Look at the address size. We jumped from 32-bit to 128-bit. That's the math behind that insane number of new addresses. But check out the other stuff. Security? It went from being an optional extra in IPv4 to being mandatory in IPv6. And setting up devices? It's gone from a mostly manual pain to being almost completely automatic. It's a total overhaul for a modern, bigger, and safer internet. Okay, but how do you upgrade the entire internet without just shutting it down for a week? It's like changing the engine on a plane while it's flying. Well, one of the really clever ways we're managing this transition is a technique called tunneling. Basically, you can wrap a new IPv6 packet inside an old IPv4 packet, kind of like putting it in an envelope, so it can travel across the older parts of the internet to get where it's going. So when you step back and look at it, this is what we have, this invisible 4-layer system that brought order to total chaos. It's this silent, organized rulebook that's running in the background every single second, making our connected world a reality. But here's the thing to remember. This amazing framework was designed for a different era. I mean, this whole thing was invented decades ago. Now we're moving into a world with trillions of smart devices, the whole Internet of Things. So it really makes you wonder, what's the next big roadblock? What's the next challenge that's going to force us to write a whole new chapter in the Internet's rulebook?